In this video, I'll show you how to work with the numerical options in Spresso. In theory, if you have a very tough electrophoresis problem with very sharp gradients, for example, you could just increase the number of grid points until it works. What I'd like to show you in this video is what's going on behind the scenes in the numerical part, so you can make much better choices on what numerical scheme you use and how you set the parameters. So here's an example. This is an ITP example that I've preloaded. It consists of an LE, TE, and a counter ion. And the way it's set right now is that it has 100 grid points. Now the spatial discretization is the standard second order center scheme. So this is a scheme that does not have numerical dissipation. It will not smear interfaces. And currently the moving frame is set to no. I'll discuss this later. And the adaptive grid is also turned off because this number is set to 0. So this is the standard way you would solve it with a uniform grid and a second order discretization. If we save this and start, in this case I've set it so that it explodes. The gradients are too sharp and we get oscillations that are way too big. This is of course an unacceptable solution. So I'm going to stop this, and now let's see how we can improve it. If I add the adaptive grid, and I can add the adaptive grid by changing the value of the adaptive grid speed. So a standard value would be 1, it's usually between 0.1 and 1 depending on the scenario, and I'll discuss this a little bit later. And let's save this and start. So you'll see the adaptive grid working. It's clustering grid points, regions of interest, but this will actually not be enough, I suspect, to solve this problem. And yes, we still get oscillations, and this won't work. So I'll stop this. So I'll remind you, this was with the second order centered scheme. Let's switch to the sixth order compact scheme. This is a much higher resolution scheme. And this should be able to resolve this problem. So again, I'm saving it and starting again. It starts the same way. The adaptive grid clusters the grid points. And now electromigration begins. And in this case, I hope it will be stable. Okay, so as you can see, you get a rather sharp gradient, but there are no oscillations, and the interface is moving downstream. So this is an example to show you the difference between the sixth order scheme and the second order scheme. I'll pause this for a second and zoom in on the area of interest. And you can see it's pretty smooth. There isn't enough resolution perhaps more grid points are required, but at least it is stable. So in general, if you want accurate solutions, go for the sixth order scheme and not for the second order scheme, because it will be faster and it will be more stable for less grid points. So now let's look at some of the other options. We have the moving frame option, which is currently set to no. Let's set this to yes and see what it does. I'll save it. I'll first unpause, stop it, and then save it under this mode. And if I start this now, you'll see that the interface no longer moves downstream. Instead, it is stationary, and we are now solving the problem in a frame of reference moving with a plug. So the way the code knows at what velocity to solve the problem in, the way it does it is that it looks at the first line of the chemicals input and calculates the velocity of that analyte or that constituent on the right border of the domain. So in this case, this is the LE. If you are solving an ITP problem then and would like to use this option, make sure that your LE appears here in the first line and that your LE is on the right side of the domain. If you have the source code, you can of course change this to use other lines or different locations in the channel. To show you why this might be useful, I change here the length of the domain to be 10 millimeters instead of 40 millimeters before, and also reduce the number of grid points to be just 70. So if I run this case again now, you'll see that we get the same solution as before, but it will be much faster because we have less grid points because the domain is smaller. But since the interfaces, especially in ITP, are typically much smaller than the size of the channel, we get all the information that we're interested in at the middle of the domain. So this is just a faster way of obtaining steady-state results. Now let's see what happens if we want to increase the current density. So I'll pause this for a second and zoom in on the interface. And you can see that the interface right now, its width is about 0.1 millimeters, so 100 microns. Let's stop this simulation. And let's see what happens when we go to higher current densities. So the interface should be sharper. So let's go to 2 microamps. Perhaps let's increase the number of grid points to 100 because we will need it. And save. Let's run this now. And let's see if we have enough grid points to resolve it. So we're on the edge, but yeah, we were able to resolve this one. Okay, so I'll stop. Let's go to 3. This should be now too sharp to be able to solve with just 100 grid points on this domain. And yeah, we get these oscillations. So let's stop and see how we can fix it. So the first thing to try is to look at the clustering level. The clustering level is proportional to the grid density at the interface. So the higher this number is, the more grid points are at the interface. But of course it is limited because it cannot deplete all the grid points from all the domain. So from some value and higher, you will not see a significant change. Usually typical values here can be between 0.1 and 5. So let me set this to 5 now. Save and start. And I hope that this will solve the problem for 3 microamps. Yeah, so looks like it was very close to getting some oscillations there, but there are enough grid points now at the interface, and this works. Okay. So the interface should be now very sharp. Let's pause this. Go in again. Yeah, so you can see it's much sharper than before, about 1/3. So this is about 30 microns. So stop this. What happens if we go to higher values? So let's go for 5 microamps. Zoom out here. Save and start. This is now even sharper. It should be a 20 micron interface, and this value of 5 is no longer enough. So we stop, and now we don't have a choice but to increase the number of grid points. So let's go to 200, and we can bring this probably back to 1. Save and start. And now, although we increase the number of grid points, this is still a relatively low number. So note that we are solving the problem with only 200 grid points, and it takes a few tenths of seconds or maybe a minute to solve this problem. So this is still not enough. We'll take it to 3. And now we are okay. So I'm not editing this video and not removing parts and showing you my mistakes as we go along to show you how to really work with this code and what's the path of thinking when trying to solve these problems and make it work. So these are the main parameters that you can use here when you want very accurate results you would first turn on the adaptive grid. You can make it faster by decreasing the size of the domain and then decreasing the number of grid points and using the moving frame. And you would increase the clustering level if you see that you get oscillations and you don't have enough grid points at the interface.